Hi everyone, I'm Thomas, and today I'm going to be essentially talking about pathfinding in 3D. So towards this end, my project is part of joint work with Woodside Energy, with the end goal being that we will be doing pipe routing for industrial plants. But towards this goal, we actually need to develop efficient methods for searching in 3D in order to actually route these pipes. So that will be the primary talk here, where essentially first we have to figure out how we're actually going to represent 3D space. So 3D space is rather large. It appears in a variety of domains: drones, pipe routing, video games. And the intuitive way to represent this might be to use some form of sparse representation, like an octree, where essentially you have high resolution around obstacles, but these large regions of open space are just represented more sparsely. But the problem here is that even though this allows really fast search, you are left with poor quality solutions, because the solutions are defined in terms of these octant centers, the centers of these very large nodes, which means you have these significant detours. So instead, we're very, very heavily interested in path quality, because that's important for the multi-billion-dollar projects for pipe routing. So instead, we're going to be using voxels, which is essentially just the 3D grid map equivalent to a 2D grid map. And so they all have uniform size. Now, this is great, but this introduces, well, inherent in this and all representations is that searching in 3D is still really hard. It's 26 connected, so it's a large branching factor. And then as part of this, you see that there's these types of symmetries in both 2D and 3D, where your path could go northeast or east-north. And so despite the fact that these have the same cost, and therefore we treat them as both very good solutions, there are many, many different ways to achieve this, and so that drastically slows down search. Now, one way to tackle this, a very well-known state-of-the-art 2D pathfinding algorithm, is called jump point search. JPS for short. And so many previous works have actually attempted to adapt JPS to 3D and have failed to achieve speed-ups due to these branching factors, or in fact they do achieve speed-ups, but they lose path feasibility. They cheat, essentially, and they use something called corner cutting. So they allow the path that they find to interact with the edges of obstacles, which simplifies the problem, but it isn't a good solution. So in this work, we developed a full translation of jump point search into 3D, which is both optimal and preserves feasibility. I won't go into the details too much, but essentially the idea is that we're performing symmetry breaking in order to remove all of these grey nodes. So this is a representation of a 3x3x3 cube just around a single voxel. We can ignore all grey nodes, and we only ever have to look in the direction of the remaining white. And so this is dependent on the direction you're searching, the angle, whether it's 2D diagonal, 3D diagonal, and so forth. And then the algorithm is really smart because we only need to bend around obstacles, which at interesting points, which we'll be calling jump points. So essentially, jump point search has a cool scanning mechanism, and it allows us to jump very quickly across open regions and simplify the space. So part of this work as well is we actually developed a novel method for bounding scan. So we ran these on maps such as these asteroid maps. We find that we're spending all of our time just scanning out into the blue yonder, which isn't important for the final path. So we developed smart ways of actually stopping that scan, stopping having to do extra work when we're moving away from the goal. Then this is kind of like an adjacent work, but we've developed this 3D pathfinding system. We achieve very, very good results on the only publicly available benchmark set that we have. And so towards this goal, we've actually developed 3 new voxel benchmark data sets. So one of these is sandstone porosity scans. The other is from a video game, but it's interior traversal this time. You're inside these winding corridors and rooms. And then we have ones taken from real industrial plant data. It's been anonymized, but is very reminiscent of both pipe routing and cityscape drone navigation, because you have these obstacles that are ground attached, so you can't go under them. Yeah, and towards this end, we see that we achieve very good speed ups, an order of magnitude on several of the benchmarks. You can observe different kinds of characteristics within each of them, which is great to see, because we're able to now estimate the strengths and weaknesses of our algorithms in different settings. And yeah, so in the future I'll be moving towards making this work for pipes itself, which means you have to consider all the safety and engineering constraints, as well as the fact that right now we're working at 10 centimeter resolution, but pipes are meant to be routed at plus or minus 2 millimeters. And so when you move towards that, you have maps of trillions of voxels, which means that it would require terabytes to store in memory, which I don't think is going to work out. So we need better methods for reasoning over even larger spaces. Yeah, so thank you for listening to my talk.